Hello, everybody, and welcome to this. Hello, everybody, and welcome to this week's Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and today I'm very excited about our hangout. We are going to be talking about the effects of a technological civilization may have on the climate of its host planet, and in particular, the effects of the effects of having a civilization like that, what those effects might be on the planet itself, and whether that civilization has any hopes of surviving those effects. My guest today is Dr. Adam Frank from the University of Rochester, whose recent paper was published in the journal Astrobiology. And the name of the article was called The Anthropocene Generalized Evolution of Exo Civilizations and Their Planetary Feedback. And we're going to address questions today like, how do we know if sustainability, which is the balance of an advanced civilization with the resources of the planet, is actually even possible in the universe? And we're going to talk about what are the possible outcomes of using the planet's resources when building a technological civilization. These are questions that Dr. Frank and his colleagues have been asking, and they've developed a model which has sort of given us some outcomes of what might happen there. We're going to talk about those today. Now, I put a link to the press release in the description box of this hangout with the link to the paper. But unfortunately, the link to the paper, all you're going to be able to read is the abstract, since you need a subscription to download the PDF file of the paper itself. But that's okay. We don't need that paper. We have the first author here himself to discuss this paper with us. So Dr. Frank is also the author of a new book, Light of the Stars, Alien Worlds, and the Fate of the Earth, which came out this summer and is available now. I also put a link to that in the description box as well. That's a book that's on my summer reading list before it ends, because I really want to get more detail into this topic. So I highly recommend that book as well for you. So that is available, and the paper is available. The link is there. But before I get going, let me just say that my co-host, Carol Christian, who's usually here, is at the IAU this week in Vienna and won't be able to join us. Well, she said she might, but I don't think she will, because it's really busy out there and the internet's not so great apparently when she tried to join the Skype thing earlier. So let me do what she does at the opening of each hangout. I need to acknowledge that these live hangouts are designed to give you guys, the general public, and all-around great space fans, access to professional astronomers directly to ask questions and become familiar with their research. This is your chance to learn what it's like to be an astronomer. They are endorsed, these hangouts, by the American Astronomical Society, whose support brings these to you every week, and the American Astronautical Society, which brings you the Future in Space hangouts that we have on every other Thursday. So while these hangouts are endorsed by these organizations, any opinions expressed here are not necessarily endorsed by them. So I needed to say that, and we'll go ahead and get going. I want to encourage all of you to live chat with us in two ways. I have the live chat on YouTube, and I also have our Discord server going. And the link to the Discord server is also in the description box. Everything's in the description box, folks. Just go there and learn about the universe, because I put all the links to all the things in there. Okay, so let me bring up my my guest. Right there is Dr. Adam Frank from the University of Rochester. Hi, Adam. Welcome to the Hangout.
Great. Thank you for having me.
I know you're very busy, and I'm really happy that you took time out to talk with us about your paper. So I did a Space Fan News on this topic a few weeks ago, where I was very curious about the nature of the model that you used, and I want to talk about the outcomes that you came to in a bit. But can you give us a general big picture overview of what you were trying to do, and then we'll talk about your model a little bit.
Okay, so what I'm interested in, I have been interested in for a while, is so along with being a scientist, I do a lot of popular writing. Written for NPR, did a blog for NPR for many years, write for the New York Times and other places. And so, I've been doing a lot of work in science population dealing with climate and the public, understanding of what's happening with climate. And in many ways, this actually came from that. What I started through my work with NPR, started getting interested or thinking about civilizations as kind of part of the biosphere, as just that any biosphere that generated a civilization might have the same kinds of things happening to it that is happening to ours. That in some sense, seeing climate change from a very different lens, what I call the astrobiological perspective on climate change. And I was interested in that, because of my deep interest. I've been a science fiction fan since I was a kid, in Exo Civilizations, but also in the sense of what's happening with us right now. What is happening with human civilization and the climate change it's triggering? And, could this in some sense be a generic consequence of a biosphere generating a technological civilization? So there was a number of papers. This paper was actually the culmination of 4 different works that we did, beginning with a paper that Woody Sullivan and I did in 2014, just outlining the basic idea that you could use astrobiology and its perspective on planets and life to inform understandings about sustainability. And then we did a second paper that came from that, where we actually did a calculation about looking at the probability associated with having having exo civilizations. Like, I'm not going to use aliens. We're done using aliens. Exoplanets and exo atmospheres, and so it's now time to talk about exo civilizations. And so, this work is actually the fourth, and in some sense, a culmination. There's more work to be done of trying to ask this question: what happens generically when a technological civilization emerges on a planet in terms of its interaction with the planet? Looking at it, again, when we think about exo civilizations or aliens, people have all these kinds of questions about, what do they look like? Are they lizards? Are they insects? That question can't be answered. Science has no way of really addressing that issue. There's no guardrails on that question. But when it comes to a civilization's interaction with its planet, we actually know a lot about planets now, from visiting, all the worlds in our own solar system. And now we're doing all this modeling and, preparing for looking at exoplanets, and we have all these different exoplanets. So we're really in a position now where I think we can start taking this question very seriously. And remarkably, it's the one thing you can say about exo civilizations, the one thing you can do some science on, is actually the one thing that matters most to us, which is our fate.
So how do you generalize that? I mean, I know we have our data point, and we can see that we're having a definite effect on the climate here on our host planet and on our biosphere. But it's hard enough to generalize things about how life even got started. But I know we're assuming if there is a civilization that is like ours, then what is it doing to it? Is that what you're asking? Because it seems like a hard thing to generalize.
Well, the remarkable thing is, what I'll argue is it's actually quite easy to generalize on a certain level. So, science is always about asking the question that you have the tools to answer, right? So when it comes to exo civilizations, there's lots of questions you'd like to ask. Like I said, what do they look like? What is their political structure like? Are they capitalists? Are they Marxists? How many sexes do they have? That's one everybody wants to know about. Like they have 8, and all of those questions, there is really not much that the science we understand can be used. There's not much we can do with the science we understand to generalize what's happened here. Because, evolution and biology are so specific. There's so many accidents, so to speak, when it comes to evolution and biology, that anything about sociology or the particulars of their biology, we just don't have the guardrails. We don't have the equations, the theory, the data points to constrain that. But when it comes to a civilization's impact on its planet, that actually is a very generic kinds of question. Because what is a civilization but a way of harvesting energy, right, from the planet? And particularly, we're going to be talking about young civilizations, meaning civilizations at our point in evolution. Meaning, and what I mean by that specifically, is that the only energy available is the energy that the planet gives you, right? So, you don't have warp drives or
Dyson spheres,
negative energy. Basically, if you live on a planet, you can burn stuff, right? Maybe there's fossil fuels, maybe there isn't. That's an open question. But you can burn stuff. There's wind, there's solar, there's geothermal. I can write down all the kinds of ways that a planet might give a young civilization energy to be used. So a civilization is just a means of harvesting energy and using that energy to do work, right? And that work is the work of civilization: irrigation, building buildings. So that's a thermodynamic question, right? That's a very sort of, fundamental thermodynamic question. And when it comes to thermodynamic inputs on planets, as I said, we have lots of data about that, right? We have Venus, we have Mars, we have complex climate models for those planets. We have Titan, which is this very different kind of system that we actually can, do climate model on. And we also have Earth over its 4.5 billion year history.
Which has changed quite a bit over the period that it's been around.
Right. Earth has been, in many ways, Earth has been a bunch of different planets, right?
Mm-hmm.
So one of the things that really struck me as I was starting to do research on this was that, when you look at, you see those animations of the continents moving around, right?
Oh, yeah. The continental drift.
Yeah, when you look at those, you see they never go back more than like 600 million years. And I was always like, well, what did it look like before that? It turns out in the early parts of Earth's history, there were no continents. Earth was a water world. There were like small islands, essentially. It took a long time for the continents to grow. What we really had first were what were called cratons, which are these sort of, Australia-sized bodies. So, Earth has been a snowball world a number of times where it's been almost entirely glaciated. So we have all of this data about how planets and their climates respond to changes. So in that way, we can model the civilization is just an impact on the planet. So we can model how planets respond to impacts because we have so many examples of planets. And then when it comes to the civilization, we can just use the most basic population biology, right? That basically, if you have an energy source, you get to multiply. And if you multiply, there's more of you and you have an impact on your environment. And if your impact becomes negative, then you die, right? That's it. So that's, I'm sorry if that was a long-winded answer.
No, that's what we want. That's exactly what we wanted. So the generalizations the kinds of inputs that your model used then was that you were able to generalize what are the possible energy sources of a planet, regardless of any of the particulars. There are certain numbers of energy sources a civilization might draw from. And then another input is the width or the age of the civilization itself. You said it was relatively young. It's relying, and by that you mean that it's only relying on the energy that the planet itself is giving it to grow. And then you just basically ran your model and came out with some possible outcomes that might happen. I want to get to those, but I guess I want to ask you first how much did our own experience go into your model? I mean, I would imagine quite a bit of our own what happened here on Earth went into this.
No, actually, not at all.
Oh,
not
really?
at all. So actually, so let's be, so let me be very specific. Our model, this model is very very idealized, right? It's a first step. So we can talk as we go on about where the next steps are. But this model was really, a stripped down version of what you'd have to do to really deeply model a civilization. So really, we had two equations. One equation was for the population, right? The civilization's population. So that's the first variable we're interested in. The second variable was the state of the planet. You can think of it as the temperature of the planet, right?
Right.
So we've got two things that we're going to follow. We're going to follow how the population is doing. Is it high? Is it low? Is it collapsing? Is it running away? And the other thing we're going to do is follow the health of the planet as gauged by, or the state of the planet as gauged by its temperature. And we'll start off in the temperature condition or the planetary state that the civilization founded in, right? So when the civilization was born, that's our reference level, right? So now each equation has parts that relate to each other. So for the population, you've got a birth rate, right? A growth rate of the population. And the way we set things up was that the population's growth rate depended on the carrying capacity of the planet, right? So the carrying capacity is a very interesting idea. It's like really how many people can Earth actually sustain, right? That's an open question. We think it's somewhere around 10 to 20 to 30 billion. After that, things are...
Do we really that high? That's amazing. I did not know that.
I mean, this is a very debatable, lots of people are, so we can get into a whole bunch of arguments there.
Right. And that's also a function of technology too, because the carrying capacity can be altered by the ability to get more yield from a crop, for example. Right. So the way in which your technological level can affect the carrying capacity of the planet as well.
Absolutely. I mean, the only reason we're at 7 billion now is because we discovered fossil fuels.
That's right, and fertilizer. And
without that, there's no way you'd have that many people. So, you know, let me actually, to be clear, the birth and the death rates depend on the carrying capacity, which in turn depended on the state of the planet. So what we had is, as the planet's state changed away from where you started, as the planet started to heat up, your carrying capacity would start to come down. Right?
Oh, yeah. Okay.
If Earth drifts off, if we get, 8 degrees of global warming, you're going to have a hard time having, 7 billion people living on the planet, because you're not going to be able to feed them. Your agriculture is going to be very difficult.
That's true. That's true.
So, and then we also had a term in there that the more people there were, that's not the right way of saying. If you then looked at the equation for the planet, we had the planet had its own internal dynamics, but there was a term in there that said that the more people there were, the more the resources were being used, and the more thermodynamic feedback you had, so the planet would heat up, right? So the population change depended on the state of the planet, and the state of the planet depended on how the population was changing, right? So they were coupled.
Good.
Right? They fed each other. And those were the models that we ran. And so in that sense, it had, we really weren't looking for the details of the Earth. We were asking a very general question, is you've got a population, they're using the planet's resources. By using those planet's resources, they're changing the state of the planet. But by changing the state of the planet, they're changing their own, the population's own ability to thrive. That was it.
Okay.
So that way I felt like, people could argue with me, that we were doing this sort of very generic model to try and just understand what are the possibilities that come out of this model, right? The beautiful thing about a model is, you can sit around and argue all night about what you think is going to happen. But when you develop a mathematical model, you understand exactly what's in it, and then you turn the crank and you can be surprised, right? The math and its interactions are going to show you what's going on. And because this was nonlinear, the equations were non-linearly coupled. It means that there really were a lot of unexpected kinds of behavior in there. And we saw that actually.
Okay. Well, what sort of things surprised you then when you ran the model?
Well, here, there was one question we had, which was, and I think this is, when I step back into my, science communicator hat, and especially somebody who's dealt with a lot of climate denial, and really trying to, talk with the public about climate. One thing I've always tried to stress is look, how do we even know that there's such a thing as a sustainable version of our civilization, right?
That is what really interests me, and I want to get to that point later. But that's amazing thought.
It's entirely possible that the universe just doesn't do long-term sustainable versions of civilization.
That is a great. Why should it? Right? There's nothing that says this has to be a thing that happens.
Right. Maybe every civilization that's born, and I would argue, we can go back to that, but I would argue that this has happened before.
Mm-hmm.
That maybe it's possible that every civilization that's born lasts for 200 years, and they go extinct because of something like climate change.
Right.
So one of the amazing things was, and what's really interesting is how when this hit the press, and this we got a lot of press for this paper. Everybody was like, climate, aliens die from climate change. Everybody missed that there were these solutions. We found there were sustainability solutions where, the population starts to rise very rapidly, as it will.
All right, hold on. Let me put this graph up, because this was taken from your paper, and it's got the 4 possible outcomes. So I'm sorry. Go ahead. It's now up, being shown, just so you know.
Okay. So the one we called it the soft landing, right? You saw the population rise. So the population's consuming the resources, and they're making more babies, alien babies, right?
Mm-hmm.
And then because there's more alien babies, there's more effect on the planet, and so you see the planet's temperature rise, right?
Mm-hmm.
But it's not like it runs away. They managed to come to a nice, sustainable, steady state. The planet has been changed, which is an important point. Everybody should know there's no such thing as a free lunch, right? If you're going to have a big civilization, you're going to affect your planet. But you manage to have a long-term energy using, right? Because energy using civilization, right? We don't want to have everybody living in the as caveman days, right? So you managed to have a long-term, high population using lots of energy, but in a planet that had reached some kind of stability. So that was really good news. It is, according to these models, simplified as they are, there is the cosmic possibility of having sustainable long-term civilization.
Okay, well, how did you get that graph? We're talking about graph B here that says sustainability on it, right, where both are growing up, but they also both plateau at a very strategic point. How did you get your model to do this? What had to happen did you have to tweak population and birth rates, or what did you have to do to get, what did your model tell you needed to happen?
The model has parameters that go into it, right? So, the population and the planetary temperature are the variables, but then there are parameters associated with all of those different interactions I talked about, right? So, one parameter is the sensitivity of the planet to having energy be used, right? So there's, either the planet, so like, this is an interesting question. It turns out that if Earth was further out in the habitable zone, we could probably burn a lot more fossil fuels without triggering climate change. We happen to be in a particularly sensitive domain. The planet's climate is in a sensitive domain such that just the fossil fuels we've already burned are pushing us into a drastic climate change. So there's a parameter associated with.
But if we just a little bit further out, we'd have a little more wiggle room on.
We'd have a little more wiggle room. Exactly. We'd have more time. We could burn more of the fossil fuels, and it would take longer to trigger climate change. So that's a parameter. There's parameters associated with the birth rates and the natural birth rates and growth rates of the population. There's a parameter associated with the planet's own internal dynamics. One of the important things to understand is that planets are machines. They're very complicated machines. And once you start it rolling, right? And once you start the planet rolling down the hill from one state, towards another state, you may not be able to stop it, right? And that's the thing everybody worries about, what they call tipping points. So what we found is, we were varying those parameters, and we were looking to see, well, what kinds of models would we get as we varied those parameters. And what we found was that there were these broad classes of trajectory. So there was a large part of parameter space for all these parameters where you get sustainable solutions. Oh. There were also broad regions of parameter space where the nastier stuff happened. So, luckily we didn't have to, none of the solutions we're showing did we have to fine tune, like we had to be like, oh my God, only these, particular values of the parameters down to 8 decimal places will give us sustainability.
That was kind of where I was heading. I was hoping this wasn't a super sensitive parameter. You had to work really hard to get graph B, because we all want graph B.
There were, like I said, now we didn't go into trying to define how broad those were. We're going to wait for the next stage where we build in more realistic, complex models to try and figure that out. But for right now, it was good to find out that it wasn't hard to find a sustaable solution.
Good. That is that, and you're right. That is very encouraging. Yeah. Let me just get one cyanide ghost has a question in here. It's relevant to this particular issue. His question is: there have been major extinctions on this planet when we're having massive die-offs of biodiversity. How does his model even make sense in view of that? Do you take anything like that into account?
No. Okay. No. But it's not. Well, here's why. Because what we're doing is we're not modeling everything that's ever happened to the planet. We're modeling what happens once a civilization appears. So in some sense, if this was the Earth, we'd only be modeling the Holocene, right? The Holocene is the last 10,000 years of planetary history, which is like, a blink of the eye, right? So we're only modeling what happens once a civilization, a technological, energy-intensive civilization emerges. So, all the previous history, whether there's been die-offs or not, don't matter for where we're starting our civilization. So maybe there have been die-offs, maybe there have been die-offs. And even if there have been die-offs, it doesn't matter. All that matters is that the biosphere has gotten to the point where it's produced a technological civilization, which is what's happened here. We had 5 major die-offs beforehand, and we still ended up with us.
That's right. That's a good point. Okay, well, let's just go ahead and run through the other 3 real quick, and then we'll move on to some other this issue of whether sustainability is even possible. The first one, you just have die-off. This is where, well, go ahead. Why don't you explain that one to us?
Yeah, okay, so that was an interesting solution, and that was where the population rose very quickly, as it does exponentially in the beginning. The planets started to change. And then what would happen was that the population overshot the carrying capacity of the planet at that moment. And so what you'd have is you'd have a very large drop in the population, but then you came to a steady state. So you could lose anywhere between 30 to 70% of your population before you ended up with a steady state. So so that was good, somewhat good news.
I was going to say, if you wanted to look for the silver lining, at least not everybody died.
Right. So what that means is that, you would go from, let's say you had 10 billion people on the planet, you'd go from 10 billion to, 3 billion over, we didn't have implicit timescales over there, but over a few generations. And, and the drop-offs could be much faster than that too. So the question, that's kind of bad news in the way, in that it's not clear that if we lost 7 out of 10 people because of climate change, it's not clear that this complex technological civilization we live in would manage to survive, right? It could be that everything just falls apart. So I mean, that's an open debate about what would happen. But that was one of the classes of solution. You would end up with something that looked sustainable, but you had to go through kind of a crisis in order to get there.
Okay, and go ahead and can you talk a little bit about the collapse without resource change and the other?
Yeah. Okay. So one of the things we built into the models was the idea that a civilization could realize that they're creating problems for themselves, and they could switch from one resource to another. Let's say there's a high impact resource like fossil fuels, and there's low impact resources like solar. And what if the civilization switched from one to the other? We wanted to include that possibility. But before we get there, let me just also note that even without that possibility, there was the most fearsome or fearful trajectories we saw were true collapse, right? Where the population rose, the planet started to heat up, and then what would happen is the planet got itself into some kind of runaway state where basically it was changing so fast that the population just, the planet moved into territory where the population couldn't survive anymore, and the population came down like a stone. True civilization collapse. And so, that's terrifying, right? That's like everybody dies. And what was frightening is that we found also a class of solutions where you could change from, the civilization could realize, okay, we got to do something. They could change from the high impact resource to the low impact resources. And it looked like things were getting better. You saw the population sort of turn over and start to level off. You saw the planet, the heating start to level off, and then boom, the population collapsed because the planet ran away. And that really shows you the importance of internal planetary dynamics, right? Again, planets are nonlinear systems. They have their own machinery, and if you push them too hard, they're just gonna, even if you think things are getting better, that machinery is still clanking away, and then it may still get into a runaway state. So that was a cautionary tale, right? That because the whole question here that we need to ask ourselves is, how sensitive is our system, right? That's one of the reasons you do a model like this, right? We want to know in general how things behave so we can see all the possibilities. And then we can look at our own system and ask, well, where are we in that spectrum of sensitivity?
And of these 4 that you were able to, that you published in the paper, were there any others, or were these just kind of the big high points? Were there
the big ones? So we talked about what do you have to, can you find, are there solutions that you have to fine tune? We actually saw we saw oscillations where the population would rise, reach a peak value and then drop by 70%, and then come back and drop by 70%. These are limit cycles, what are called limit cycles in the language of. So this whole branch of physics would be what's called dynamical systems theory. And so limit cycles are a kind of solution you can find. And so those ones kind of needed fine tuning. So.
Okay, there is so much in this research and in this model that is enveloped into the parameters that you used. But like for example, the ability of a civilization to make decisions in an efficient, timely, reasonable manner and decide for itself whether or not it can do these things. At least you're showing that it is possible for a civilization to be sustainable. But I would like to ask you, because this is something that I still think about it, even weeks after I first read about this, is that when you think about the universe as a whole, there's nothing about it that is sustainable. I mean, stars they reach an equilibrium. They live for a while. They blow up or they just die. And the most sustainable star is probably a red dwarf. So the universe itself isn't acting in a very sustainable way. It's accelerating and as it expands, it may just eventually evaporate into nothing, or black holes or whatever. What do you think about, and I know this is just an opinion, but what is your thoughts on this issue of sustainability? Is it something on a level of a civilization and a planet that's even really possible? Do you think we can do this?
Well, I think so sustainability is a relative term, right? I mean, human civilization, and by civilization, I mean, agriculture, city building, obviously we were hunter-gatherers for a long time, and that's a kind of civilization.
Sure.
But I'm really referring to this sort of organized, what I call the project of civilization, this big communal project. And so we've been at that for about 10,000 years. The industrial part's only 200 years. years old, right? So look, if we got another 1,000 years or 10,000 years or 100,000 years, that would be pretty awesome, you know? And by the time you get to those timescales, who the hell knows what's next, right? There could be all kinds of, there's going to be a whole other range of existential threats that, you know, we could incur that we can't even imagine now because we don't know what kind of technology. So for me, you know, my concern is that we make it at least another few thousand years to get to the point where, like, we can deal with it. You know, we can get ourselves to the point where we can encounter the next existential threat. You know,
it does seem like that's the time scale, doesn't it? The next 1,000 years are going to be the difference for us, isn't it?
Yeah, that's really what I mean. The next 1,000 years, I think, will tell us whether or not we have the capacity as a species. Because really, the next 1,000 years, if we make it, is going to be the solar system, right? We're going to spread throughout this. That's what I would argue. We're going to spread throughout the solar system. You know, we will have managed to build a sustainable version of human civilization on Earth. And then, you know, where else is there to go but the solar system?
Right.
Stars are a long way. It's going to be a very hard trip to, you know, unless a miracle technology like warp drive, you know, is invented. We're stuck in the solar system for a while. But yeah, thousands of years is sort of a time scale where you can imagine that we've changed enough, that technology's evolved enough, that there will be a new set of problems. So we got to kind of, and will we even be human still then by then, given, you know.
Well, if Ray Kurzweil has his way, no, we're going to be.
We're I have issues with that. But in general, I certainly would agree that
too.
A few thousand years, especially with genetic evolution, you know, that it could be, you know, it's going to be a very, all I can say is it's going to be a very different set of questions after 5,000 years. But if we just need to make it that long so we can get to that point and see what those next set of questions is.
Did you find in the course of this, in the communication that you've done after the paper came out, did you find anybody accusing you of being political in this, trying to make some kind of political statement about climate change and global warming? Because I did when I did a story. I do this news Spaceman News episode where I talk about the latest research and I pick a topic, and one of the topics was your paper, and I said that you know, this is a really good model for us to use here to decide what to do about our own planet. Did you get any pushback on that from anybody, or was everybody's like, yeah, we really should probably pay more attention to climate change?
Well, I've been dealing with climate change denial for a long time.
I'll bet you have.
I'm unrelenting about it. I mean, you know, anybody who's got a problem with like the science of climate change, you know, needs to how do I say this and be, you know, needs to like read a book. Okay. You know, I mean, the science of climate change has been decided now for decades. You know, anybody who's like still saying that, you know, the science is undecided, or God forbid, you know, the worst, when we hear this all the time, it's a hoax, or is like, you know, check your politics, right? Check your tribalism at the door, because this is science. Now, you know, there's a whole bunch of questions about politics that come once you've absorbed the science. Like, what do we do about climate change? Oh, that's a political question. And that depends on what political party you're part of. But the science part of, you know, like I say, the fundamentals of climate change are we change the climate, or the climate is changing, and B, it's changing because of us. That part is so firm and so decided that if you got a problem with it, then, you know, hand in your cell phone, okay? Because it's not fair to be like using all the fruits of science, you know? That's what I find with a lot of climate change denialists. It's sort of like, oh, you know, they run to the doctors and they're like, oh, give me some antibiotics because I feel sick. But oh, climate change, that's a bunch of hooey, you know? It's unfair, and it does great damage to the American scientific enterprise. Okay? So there's absolutely politics involved in here, but it has nothing to do with the scientific part of the conclusions.
Right.
So, you know, you got to separate those two so we understand what we're dealing with, right? And there's, you know, when it comes to uncertainty in climate, you know, there are questions that are, you know, of course, it's science. There are places where the science is uncertain. But is the climate changing? That's not uncertain. Is it changing because of us? That's not uncertain. You know, exactly what's going to happen, that part's got uncertainty in it, and that's the part where we try and do our understanding, and we're making bets on the future for sure. But is the climate changing because of us? That part's nailed.
Right. There's been plenty of surprises about the future of what's happened once we've discovered that the climate was changing. Certain glaciers, certain melting points are happening faster. Things are occurring at rates that were totally unexpected, and things have had to be adjusted. So that comes from what you were saying about it's hard to figure out what's going to happen exactly. Right. We have a general picture, and it's very concerning, but there are a lot of indicators that this is happening in ways we didn't expect.
I mean, this summer, fire tornadoes, right? There's a new word for
it. I know.
Fire hurricanes, But let me say, my view on this, I have, from this, I feel that the astrobiological perspective that we're working with here changes a lot of how we look at climate change. Like, so for example, here's something I'm going to say that makes people angry, which is that, climate change is not our fault. And here's what I mean by that. Triggering climate change. We didn't trigger climate change because we're a bunch of evil, greedy, monsters who, are like, I want to destroy the planet. The whole history of civilization is us using whatever energy source we could find in order to power civilization. It was animals, it was animal poop, it was wind. And when we discovered fossil fuels, we were like, this stuff is awesome. You can heat your house. You can make internal combustion engines. We didn't trigger climate change because we're greedy. And that's one of the things, this narrative of human beings being, greedy, a plague on the planet, from the astrobiological perspective, that makes no sense. We are what the biosphere is doing now, including triggering climate change. We are in some sense nature's way of triggering climate change, right?
Yep. And I think you're right on that. The only thing I would add to that, though, is that while human beings aren't necessarily being evil and just consuming and doing it in any sort of malevolent way, the same could not be said for a lot of the techniques we use for harvesting these resources in the form of corporations, which really do have a much more vested interest in themselves than they do in anything the planet might have to sustain.
It. That's exactly it. It's triggering climate change was not our fault.
Right.
Not doing something about it will be our folly. Yes. Because now we've been warned. We've known now for 30 years. And, anybody who's still arguing that we shouldn't be doing something about it, they're going to be the reason why we don't make the step that, I like to say that climate change is, it's our adolescence. It's the beginning of our adolescence. We've matured as a species to the point where we've changed the chemistry of an entire planet, which is not bad for a bunch of hairless monkeys, right? Climate change, there's a certain level at which we can be proud of triggering climate change. It shows we've risen up the ladder of civilization development. But if we don't see what we're doing and take some drastic, measures soon, then we're just going to wipe our, the planet will move on without us. The planet's going to be fine.
Right. I say that too.
Right, exactly. The planet's going to be just okay, but it's whether or not the project of civilization continues. So, this, for me, the astrobiological perspective completely flips the script on climate change, because most climate change deniers are like, oh, you're just a bunch of tree huggers, you care more about the environment than human beings. And from my perspective, climate change shows human beings are awesome. Look what we did. Now let's be even more awesome, and figure out how to come into a cooperative relationship with the biosphere in a way that doesn't practice ecological hooliganism and then doom ourselves.
And that brings me to this idea of, we talk a lot on this channel about the great filters. These are this idea in response to Fermi's question, where is everybody? I have gone from thinking, well, there's so many stars, so many planets, 1.6 planets for every star in our galaxy. We have there, of course, there should be other civilizations out there. I've gone from that thinking to thinking, wait a minute, we might be the only one. And the reason I'm getting to that point is that there are a lot of what I think are great filters. And before I read your paper, the one that I felt was going to get us the most was that stood in our favor was, is life common, or is life easy to start from nothing? That to me was a great filter. I think it's hard to go from no life, building blocks of life, primordial soups, to something that's alive. I think that step is hard. I think that's a filter. But we've gotten past that one, thankfully. Right. But another one is our biology and going into space. You said that we should, if we get through these next 1,000 years, the next space is the solar system. I'm not so sure. I think our biology might prevent us from surviving in space unless we do something Ray Kurzweil about it and make it not an issue. And finally, so this issue to me though is one that I feel is even more important than that. Do you think, based on your research and your thinking about this in the context of your paper in astrobiology, do you think life is common in the universe, and in particular civilizations? Do you think this is not such a big deal?
Common, I mean, because so that was this paper I did with Woody, where we this other paper where we looked at use the Kepler data to, and again, always with science, what question can you answer? So we used the Kepler data and we manipulated the Drake equation to answer this question, right? How bad do the odds per habitable zone planet have to be for us to be the only time it's ever happened in the universe? Okay, so we were able, by manipulating this, we were able. So that's a question we could set a limit on. And it turns out that unless the odds for developing a civilization are less than 1 in 10 billion trillion, then we're not the only time it's happened, right? So to frame that better, because it takes a little work on this.
Yeah, I'm still thinking about that.
So we don't really know what you take a planet in the habitable zone, right? You pick a random planet. Nature, nature has all these evolutionary processes, as you said, for first forming life, and then going on to evolve intelligence, and then intelligence going on to form civilizations. We don't know what nature actually sets those probabilities to be. It's going to be, it's going to be a whole bunch of processes that we just don't have any access to. But with the Kepler data, what we could do is we could set a limit, and we called it the pessimism line, where we said, look, what we can actually figure out from the Kepler data is where does nature's probability choices of probability have to fall for us to be the only time it's ever happened? And what from the data, it shows that it has to fall on less than 1 in 10 billion trillion, right? That 1 in 10 billion trillion is a very, very, very small number. So as long as nature's processes conspire to be bigger than 1 in 10 billion trillion, then it's happened to us, like civilizations have happened before. So from what I drew from that, and I did this, we did a New York Times op-ed on it where they ran the headline as being, yes, there have been aliens. And I would have said, yes, there probably have been aliens. But that generated a lot of controversy. But that's an empirical limit. That's the first time anybody was able to set an empirical limit on this probability. And so it turns out it's because there's so many exoplanets in the right place for civilizations to form.
Yeah, and what Kepler told you was that there were this many planets probably on average, and that there's certain, based on what Kepler found, might be this many in a habitable zone. I don't get how you went from there to 1 in a billion trillion chance of there not being any other civilization.
Because what you do is, it's really just what you do is you take Kepler's numbers for how many what's the average number of planets in the habitable zone, which turns out to be 0.2, right? Okay. You count up 5 stars and one of them has a planet in the habitable zone. Now count up all the stars in the universe, right, since the dawn of time, and multiply it by 0.2, and you get the total number of habitable zone planets in the universe, which is 10 billion trillion. Every one of those planets is a planet where life and intelligence and civilizations could have formed. Every one of those is an experiment. So nature has run, and we know this now, right? Those numbers are pretty firm. Nature has had the opportunity to run 10 billion trillion experiments in life and civilizations, right? So in order for us to be the only time it's ever happened, every one of those experiments have to have failed, okay? So it's a very simple thing. Now, of course, what's not included in that, right? We had to, in order to do this calculation, we had to drop the lifetime factor in Drake's equation, right? So what that number tells us is that what has happened. It doesn't say what's happening now, right? Sure. It could be, if every civilization lasts 200 years, then yeah, there's probably nobody around now. But what we get from that calculation is that there probably have been lots and lots of experiments in civilizations. And that's what matters to me from this calculation, right? Because what I wanted to know is, what is it, if I have an ensemble of civilizations, if I have a big collection of civilizations, then what's their average kinds of trajectories? And that's what the model gave us. So what that the 1 in 10 billion trillion tells me is, you know what? Unless nature's really perversely against it, then there have been a large ensemble of civilization.
Well, hold on though. You said that this is that's had 100 million or billion trillion chances at success. Well, we know there's been one, right. But that's really, I mean, so it's okay. It worked, but there wasn't necessarily 100 billion trillion civilizations out there that just had that many chances to make one.
But as long as, but again, this is where, so if you could do it, if you somehow had God's computer and you could, somehow know all the laws of physics to a perfect, and you could calculate what the probability per habitable zone planet was, of forming a civilization, what our empirical results showed was, as long as it was bigger than 1 in 10 billion trillion, then what has happened to us has happened before. Okay. So if a pessimist wants to say, look, we're the only time it's ever happened, they have to show that the probability per habitable zone planet is smaller than 1 in 10 billion trillion. So that's why we just argue that, the numbers here are overwhelming, that it's I can't tell you how many times it's happened before, but it's probably happened before. And it doesn't mean anybody's around.
And again, you're talking about the entire universe.
Exactly.
And so
the galaxy, we could easily be the only civilization in the galaxy right now. I would have no problem with that.
Okay.
But the idea that it's happened, so again, what I'm concerned with in this paper was, I want to know whether we're going to make it. Right?
Yeah, me too.
So I wanted to know, just so in my book, I start the book off with this image of a bunch of teenagers in an encounter group, right? And they've all had problems. They've, stole cars or whatever. And, when you don't have, for a teenager, if you don't have anybody else to talk to, you think like, oh my God, my life sucks. Nobody knows what my problems are. And then you talk to other people who are like, oh, other people have histories like mine. It's, I can use that. I wanted to do the same thing for civilizations, right? Because we think we're the only time it's ever happened and we don't know what's going to happen. And what I'm saying is that, probably this has happened before, and we can try and learn from those other histories, even if right now only by doing the modeling.
I think that's a great point. Okay, let me ask you Juan Astorga Wells's question. Considering the current population and energy growth, as well as our planetary resources, how much time has the Earth before it's too late? Can your model predict this?
I would say right now my model cannot predict that, because the model doesn't have that the model was not specific to the Earth. So when, again, I want to be careful when you say how long for the Earth before it's too late. The Earth's going to be just fine.
Yeah, that's
right?
an important point.
So even if we trigger a mass extinction, right, that's not the end of the Earth. Remember, the only reason why we're all here is because of the last mass extinction, right? Before the last mass extinction, there were dinosaurs everywhere, and mammals were hiding in the shadows. And it was the last mass extinction that allowed the age of mammals to begin. So mass extinctions don't end the biosphere. The biosphere actually kind of uses them to create new niches and do more innovation.
It's refreshing.
Well, from the long-term biosphere perspective. Now, that's not a license for us to practice ecological hooliganism. That's what I always have to say when I show that.
Yeah.
The real question is, how long do we have? Right?
Yeah.
The question is, if the Earth's climate drifts into some other state, because it's been in some very crazy states in the past, it's going to be it's hard to imagine human civilization of the kind we have surviving. And that question it's hard to say, but look at what's happened this summer, right? We are just beginning to see what climate change looks like. And and in Seattle right now, or at least yesterday, breathing the air was like smoking 7 cigarettes a day, because of all these forest fires. So, I would say that if we don't do something pretty radical pretty soon, it's gonna, we have a couple centuries at most, or it's gonna. I mean, I don't. It's very hard. As Yogi Berra said, the prediction is hard, especially about the future.
Here's how I'll give you an economic. Here's how it started. Red flag. When you go to South Florida and Miami and buy a house and you can't get insurance on it, that's when you know that the beginning of the end has begun, because insurance companies are going to know, and well in advance, and they're not just going to give a mortgage out on a house that they think is not going to be around in the short term. So look for those. When mortgages start getting hard to get in South Florida or Myrtle Beach or wherever it is that's on the coast,
Yeah.
That's a red flag.
Yeah.
Let me get to Launchpad Astronomy. He is asking, what are the timescales in the models, or were they iterations? And you said that you weren't very clear on the timescale of your model.
Well, because the timescales are, it's in the parameters that we were using dimensionless parameters, so we had a dimensionless time. So we'd have to go back and actually put in real physical values, and the models aren't there yet.
Okay.
What I can say is the collapse was very sudden. The collapse would have been over timescales that were short relative to the generations of the biology, right? But there weren't inherent timescales in the model. So let's just talk for a second about the future of the models. What we want to do now is actually build in real climate models, real physical models, real, some very super simple biological sort of biological models in there. So in the future, we'll be able to do this and actually include real time scales and get a sense of for a given planet, what is its probability of going into one of those different zones.
And you kind of did that with population a little bit. You said, at least the press release, I read that you used an example of Easter Island, which I think a lot of people had some issue with, as a possible model for the population.
Well, the interesting thing is we took some of the, when I am not a population biologist. I'm
right.
a numerical fluid dynamicist. So when I started, working on this, I had to go into the literature and learn the literature of population ecology, which was awesome. And, when I finally found the piece of the model that was really important to me in models of Easter Island, people modeling the collapse of Easter Island's society. So that was kind of an interesting, and Easter Island is like the example of civilization collapsing. Now, of course, with Easter Island, everybody knows it's complicated, but I mean, it's, I've been reading the literature and it's hard. Easter Island, the eco side played a role. There may have been other things going on, but the overuse of resources, the consensus I think still is that played an important role, if not the quintessential role.
Yeah, that was the thing I had to explain a lot too, was that Easter Island was more complicated than just using trees and resources and dying off. One plot. I'm going to try and read your question, but I'm not sure I understand it. If a similar species as humans existed on a super Earth, would they reach the same developmental timeline as us? Hence population plus technology, and then carrying capacity less impacted due to the planet's size. So I think he's asking, if we did this on the super Earth, you had already mentioned if we were just a little bit further out in the habitable zone, we'd have a little more wiggle room. Does the size of the planet give us more wiggle room, perhaps?
Yeah, that's an interesting question. The problem with population growth is, especially when you're not resource limited, is it's exponential. So you pretty quickly, having a planet that has 6 times more surface area isn't going to help you for very long during that phase of super rapid population. Think about it. We crossed the 1 billion mark just in 1850, right? So there's more people living in a small size city now than lived on the entire planet before the birth of agriculture. So our population has been this. Yeah. So it's a great question. That is a super cool question, and I'm really excited about modeling different kinds of planets. But I think my gut reaction is the exponential phase overwhelms your increased surface area.
Yeah, and that I want to get to Angel Views. Okay, Angel's View has a comment. There is no such thing as sustainability. This is a planet Earth where toxic chemical corporations destroy ozone and life. There is where you dream of, and there's what you dream of, and then there's what's actually happening. And that's my concern too, Angel's View. I believe in what Adam has said is true about humanity's intentions, but there are other forces that scare me and that are motivated by things other than their own survival. They're motivated by profits, and at the expense of common sense things like, well, how are you going, or how sustainable is this going to be in the long run? And that's my worry, is the short-sightedness of all of this. Another thing that's not really talked about here was something Carl Sagan was worried about a lot in the 80s, which was things like technology destroying us, and that's another topic, but that was sort of related. He was very concerned we were going to blow ourselves up and not make it. So for him, a great filter was nuclear annihilation.
Nuclear war, yeah.
Yeah, so...
Bill,
by all means, yeah, go ahead.
I mean, listen, I think climate, again, if climate change, I'm going to argue it is a generic outcome of having a civilization, like that anybody who, any species that develops technological civilization triggers climate change, then whether or not you make it through or not probably depends on what your evolutionary baggage is, right? So you can imagine maybe if you're a hive mind, if it's intelligent termites, that it would be easier for them to get their act together and act collectively. So either it's what, evolution gave you in terms of your behavioral characteristics, or it's your ability to evolve new behaviors, right? So climate change is an evolutionary pressure, right? So now I'm no expert in evolutionary biology, so people can yell at me, but my understanding is that evolution happens when there are pressures applied to species. And climate change is a pressure that's being applied to us. I have no idea if we're going to make it. I certainly hope we do. But this is the moment when these behaviors, that have both served us well and not served us well in the past, where like some of them we're either going to figure out how to change. The Paris Accords, as weak as they were a very interesting step. Like the whole world, managed to get together.
I couldn't believe it. I know.
So that was like, oh, maybe it's possible for us to develop, these kind of collective behaviors.
A consensus of some kind. Yeah.
Okay. Yeah. Right. So, we'll see. I hear what you're saying, and this is as one climate scientist put it, climate change is humanity's final exam.
Yeah. Yeah, and it is a great source of pressure, and we'll see if we're up to the task or not. It'll be an interesting next 1,000 years or so. Well, all right, I'm going to go ahead and stop here. I want to thank you, Dr. Frank, for taking time out to talk about it. He is a professor at University of Rochester, and his new book is called Light in the Stars, Alien Worlds, and the Fate of the Earth. It's available now. The link is in the description box. Go check it out. Lots to think about here, folks. Let me know what you think. Even though the live stream is over, I'm still looking at your comments and questions. Please leave them here in the comment section, and if I don't know the answer, maybe I'll bother Dr. Frank with an email, and maybe he might be able to answer it for you. Otherwise, I want to thank you all so much for watching. Next Thursday, we're back with the Future in Space Hangout, where I think Harley has got on tap. We're going to be talking with people from NASA on the Parker Solar Probe. So we're going to see how it's doing coming after it on its way to the sun. So check in next week, and I will see you guys later. And thank you all so much for watching. And as always, keep looking up.